All right, guys, so what we're doing today is finishing the note sheet from yesterday. So yesterday we talked about transformations of quadratic functions, moving the function up, down, left, right, or describing how it moved up, down, left, right, stretch, shrink, all of that there. And what we're doing today, we're going to talk about two things. One of them is going to be vertex, talking about vertex and vertex form, how to identify the vertex, and applying transformations to a function. So, the vertex of a given function is the point h comma k. H comma k is the vertex. Now, the vertex is the lowest or highest point. It would be considered the lowest point if the parabola opens up. This here would be the vertex. And if it opens down, the vertex would be the biggest point. So if it opens up, the vertex is the smallest point. If it opens down, the vertex is the highest point. And it's helpful with graphing because the vertex gives us our first point, and then we can do 2 points to the left or right from there, if you want to follow along. Now, right below that spot, I want you to put these three here. Yep, so right there. So right underneath there, you can put these three equations. Yep, so right there. Because I added this here so that we get some practice with identifying the vertex. Because up to this point, we haven't done much with identifying what the vertex is.
Well, we write that down.
Yes. And the vertex is the point h comma k. Bless you. So if we know what the values of h and k are, we can find the vertex. So if we leave this first one here, g of x equals 1/2 times x minus 1 squared. So looking at this first one here, what's the value of h? 1. Would it be positive 1 or negative 1? Positive, because x minus h, x minus 1, so h would indeed be 1, positive 1. What's the value of k?
0.
There is no k value. There is no number being added to it, so it would be 0. Now for our k tells us how far we move the function up or down. When we describe the transformation, we wouldn't say that the function moved up 0 or down 0. It's not telling us anything. However, with the vertex is a point. It's an ordered pair. So having 0 as a part of the ordered pair actually tells us something. And the vertex is the point h comma k. Well, h is 1, 0. H comma k, 1 comma 0. 1, 0. And yes, we can't have a vertex at the origin at 0, 0. The parent function f of x equals x squared, y equals x squared's vertex is 0, 0. Yeah, so the second one, h and k, so our h value would indeed be negative 10, because since it's x plus 3, really what we're looking at is x minus negative 10. So h is negative 10. K would be negative 3, telling us that the vertex is the point negative 10 comma negative 3, our h comma k. So being able to identify the h and k, especially at this point, is going to be helpful. Because when we start talking about these parabolas more, and especially in vertex form, knowing what goes where is going to be very helpful. negative 4 times the quantity x plus 1 in quantity squared minus 5. H comes from inside our parentheses. Since it's x plus 1, h, 1 is in the place of h, but would it be positive or negative? Negative, because the only way to go from x minus h to x plus 1 is if the value of h is negative. What's our value of k? Negative 5. In our vertex, the point h comma k would be negative 1, negative 5, h comma k. Questions on this here? Questions? We understand how to find the vertex. And vertex is nice because if we were wanting to graph or graph a parabola, we need 5 points. And the first point, or the main point that you need for a parabola is the vertex. Vertex is the highest, lowest point. The rest are going to kind of follow in line. Because once we have the vertex, in this case 1, 0, we would get 2 points to the left, 2 points to the right. And that will help us see what the shape of the parabola is. So it kind of helps us get in line. It also helps us see and get a picture of what this looks like. We know it opens up is if the value of a, the number in place of a, is positive. It's going to open up. If the number in place of a is negative, it's going to open down. The only thing that we're going to do for the rest of the class, we have 3 problems that we're going to do. It's going to be applying these transformations and identifying the vertex. So if we look at problem number 1, let G be a vertical stretch by a factor of 2, reflection in the x-axis, followed by a translation 3 units down. So the first thing we want to apply, all right guys, focus up here, up here. Vertical stretch by a factor of 2. Now the general form for this is our a times f of x. And we can call this function h of x. Where a is the amount that we're stretching or shrinking the function by. And since it's a vertical stretch, we can just take that value that they told us and plug it in for a. So a would be 2. As it says it's a vertical stretch by a factor of 2. So our reflection, the general form for reflection across the x-axis is negative f of x. And we'll apply that here in a second. Now at this point here, we've plugged in our transformation parts for the vertical stretch of 2. Now we can replace f of x with what it equals. And f of x is x squared. So we replace f of x with x squared, and we get 2 times x squared. The last thing we need to do is simplify. We can multiply these two together, and 2 times x squared is 2x squared. Because 2 times x squared is 2x squared. Now, the next transformation is reflection in the x-axis. Now, the general form for this here, reflection in the x-axis, would be negative f of x. But we're not applying it to f of x anymore. We're applying it to h of x. I'm going to call this new one m of x. It really doesn't matter what we call it. Now, we're applying that reflection across the x-axis now to our 2x squared. So reflection across the x-axis is our negative h of x. Well, h of x is 2x squared. Really what we're doing is we're multiplying that negative through the entire equation. For reflection across the y-axis, we're plugging that negative x in for x. We're replacing x with negative x. Here, we're multiplying through. And negative times 2x squared is going to be negative x squared. So we've done the vertical stretch by a factor of 2. We've done the reflection across the x-axis. What's the last thing we need to do? Translation what? 3 units down. Now the general form for moving a function up or down is our f of x plus k. However, we're not applying it to f of x, we're applying it to m of x. Now the amount that we're moving up or down is indeed 3, yes? Could it be plus 3 or minus 3? Minus because we're going down. Now that we have everything plugged in for our transformation, we can replace m of x with its function. So we have parentheses negative 2x squared, close parentheses, minus 3. Do we still need the parentheses? No, so we can drop the parentheses, telling us that we have squared minus 3. We'll call this g of x. Really doesn't matter what we call it, but this is how we get to this point here. So we finished all of our transformation, yes? So we wrote the rule. Now we just need to find the vertex. The vertex is the point h, comma, k. So k indeed would be negative 3. Now you're saying h is 0. Why would h be 0? There is no value in place of h, yes? For us to have h, we have to have parentheses. We have to have the parentheses with that square on the outside. So since we don't have parentheses around that x in front of the square, it is 0. Because really, if we match it up completely, we would say that it's negative 2 x minus 0 squared minus 3. We don't write x minus 0, because x minus 0 is just x, yes? Because x minus 0 is the same as x. Then at this point, we don't need the parentheses around it. It's just going to be x squared. So our vertex is the point 0, negative 3. Questions on this here? Now, doesn't it feel like we just stuck negative 2 in for a and negative 3 for k and called it good? And for the most part, that's what happened. But the reason it happened that way and the reason it worked that way is because the transformations were put in the order that they were. Because they said that we had a reflection across the x-axis and that vertical stretch of 2 first. That happened first. They're both being applied there. Then we moved down 3. Stuck the minus 3 on. And it works that way because of the order in which the functions, these transformations, were applied. If we did it the other way around, went down 3 and then applied the vertical stretch of 2 and a reflection across the x-axis, we would have ended up getting negative 2x squared plus 6. It would have given us a different function because of how they work, how they interact with each other. Because they were put in this order, it works just fine. So why didn't we do it that way? Well, because I like showing you a way and I like going over ways that work every time, no matter the setup. So I don't like doing it that way just because it works this way. I want a way that works even if we translated it 3 units down first and then did the vertical stretch and the reflection. I think it's better to learn it that way than to learn this one specific case. If it's ordered this way, it works. Ordered another way, it's not going to work the same. Questions on this here? This next one's kind of nice because we only have 2 transformations. Let G be a vertical shrink by a factor of 1/2, followed by a translation 2 units up. And again, I will show you this here. It's going to get to the same spot because according to the book, we would plug 1/2 in for x, a, 0 for h, and plus 2 for k, and simplify from there. Which will work, but let's look at it. Vertical shrink by a factor of 1/2. So the general form for this is a times f of x, where a is the amount that we stretch or shrink the function by. So we have 1/2 f of x. At this point here, we can replace f of x with its function, which is x squared, and then we multiply it, giving us 1/2 x squared. Translation up and down, f of x plus k, or in this case, h of x plus k. Because again, f of x, h of x, g of x, m of x, n of x, and z of x. Just a way to name the function. What's our value of k? 2. Positive or negative? Positive because it's going up. It'd be plus 2. H of x. We can replace it with its function. So we'd say h of x is 1/2 x squared. Is there anything in front of the parentheses? Any exponents? Anything attached to them? Do I still need them? No. Oh, we have 1/2 x squared plus 2. Do we have any other transformations that need to be applied to it? So we have our function, vertex. What is h? 0. And k is positive or negative 2? Positive 2. So the vertex is the point, 0, 2. And that's it. Questions on this here? And again, I like this method because even if they gave us a function that's just not x squared, we had 3x squared plus 2, we could still do this. It still works. Still is the same thing. Questions on this here? You ready for the last one? Let the graph of G be a horizontal shrink by a factor of 1/3 and a reflection in the y-axis, followed by a translation 2 units up of the graph f of x equals x squared. Horizontal stretch or shrink, our general form is f of ax. F of ax, where a is the amount that we stretch or shrink it by. Now it told us it's a horizontal shrink by a factor of 1/3, yes? So the value that we plug in for a is not going to be 1/3. What would that value be? It would indeed be 3. Because we have to take that horizontal stretch or shrink, whatever the amount it is, and flip it. We have to flip it. So even though it told us it's a horizontal shrink of 1/3, the value that we plug in for a is 3. We have to flip it. Well, I don't have f of x anymore. We have f of 3x, yes? Which means every x in f of x, we have to replace with 3x. So we had x squared. Now we have 3x squared. Now at this point here, we're going to leave it alone because we want to get this and leave it as close to vertex form as we can. Since we have parentheses around it, that's still inside the parentheses, our value b, we're going to leave it alone. I'm not going to apply that power of 2 to it. Because we could, that would tell us that it's 9x squared. We'll leave it as 3x in parentheses squared. So that's our vertical stretch. Horizontal stretch by a factor, shrink by a factor of 1/3. First part done. Now we have a reflection in the y-axis. Now, reflection of the y-axis in the general form is normally f of negative x, but we're not applying it to f of x, we're applying it to h of x. So we can say it's h of negative x. Kind of like what we just did for horizontal shrink. We're going to replace every x in h of x with what? Negative x. So I would still have my parentheses 3, but instead of x, we have negative x. Interestingly enough, we're going to multiply those two together. 3 times negative x is negative 3x. I'll call it m of x. Because the last transformation we have is what? Up 2. So we can say m of x plus k. And just like we've had before, our value of k would be plus 2. Now, we could put a set of parentheses around our parenthesis negative 3x squared, but because there's nothing in front of those parentheses, we'd get rid of it, which would get us back to this point here. What's our value of h? 0. What's our value of k? Positive 2, yes. So our vertex would be the point h comma k, which is 0, 2. And that's it. Questions on this here? Don't write this. Okay. So I added a value in place of h, yes? So what would the value of h be now? Because the number would be 3, yes? Would it be positive 3 or negative 3? Negative because we have the x plus, yes? Or the plus 3. So with how we've been doing this and how we look at this, we would say negative 3 comma 2, yes? Now I did say earlier, having a horizontal stretcher shrink and the reflection across the y-axis, I believe I said in here, kind of messes with our horizontal translation a little bit. Now, let's look at the graph. Now, I did go on and plug this in here, negative 3, x plus 3 squared plus 2, yes? So we graphed it. I can go second table, and I can look at points. So it's already done it for me. Because when x is negative 3, the y value is indeed 2, yes? What does it say the y value is? So at negative 3, it says the y value is 146, yes? Well, wait. Vertex is supposed to be the highest or lowest point. Highest point if it opens down, lowest point. Highest point if it opens down, lowest point if it opens up, yes? This is opening up. That is not. Negative 3, 2 is not even on the graph. And negative 3 is not even the right x value for the lowest point. What I'm going to do is I'm going to factor that negative 3 out. I'm going to pull it out of both terms. The negative 3x and the 3. Because negative 3 factored out of negative 3x is x, yes? If I factor a negative out of a positive, it's going to become negative, yes? What happens when we factor a 3 out of 3? It becomes 1, yes? So if I factor that negative 3 out, we get negative 3 times the quantity, or times x minus 1, yes? Looking at it now, what's the value of h? Positive 1, yes? So removing that negative 3 out, it changes it from 3, negative 3 to 1, yes? Let's look back at the graph. Wait, 1, 2, yes? 2 is the smallest value of those y's because they're all going up. That is the vertex. 1, 2 is actually the vertex. That's why I was saying earlier why having that horizontal stretch or shrink, and especially having this with the reflection across the y-axis, why it messes with what the actual vertex is. It messes with it. Now for this here, you're not going to have one that has a vertical or a horizontal stretch or shrink and a horizontal translation. You're not going to have both. Just because this messes with what it actually is. So, that's it. Homework is problems 3 through 11 odd, 17 through 21 odd, 27 through 29, 31, and 33. So 3 through 11 odd, you just need to describe the transformation. That's it. Do not graph. 17 through 21 odd, describe the transformation. You do not have to graph. 27 through 29, describe the transformation and identify, label the vertex, say what the vertex is. 31 and 33, apply the transformations and identify the vertex.